If you look at the sky at night, you'll see many small bright spots. One of them is Andromeda, our neighbouring galaxy. What most people forget is that what we're seeing isn't the Andromeda we see today, but the one from 2.5 million years ago. This is because it's 2.5 million light years away from us, and that's how long it took the light to travel to reach us. But what does 2.5 million light years actually mean? Numbers of this magnitude simply defy our imagination. Let's try to make it more tangible anyway. 1 light year, the distance light travels in 1 year, is about 9.5 trillion kilometers. Multiplying that by 2.5 million gives us a distance that no human brain can truly grasp. Imagine the Earth were a marble. On that scale, the Andromeda galaxy would be about 50,000 kilometers away, more than once around the real Earth. Or to put it another way, if we were to shrink the entire distance to the Andromeda galaxy to the length of a football field, the distance between the Earth and the Moon would be just 1/10 of a millimeter. Not even the thickness of a sheet of paper. And this is precisely where our fundamental problem begins. The universe has imposed an absolute speed limit on us, the speed of light. Approximately 300,000 kilometers per second. That sounds incredibly fast, and it is. Light circles the Earth 7.5 times in a single second. But even at this insane speed, it would take us 2.5 million years to reach Andromeda. And unfortunately, it's not even possible for us to travel at the speed of light. The theory of relativity tells us that nothing with mass can ever reach the speed of light. The faster an object goes, the more energy it needs to go even faster. As we approach the speed of light, the required energy would approach infinity. And this is where it might get a little complicated for some, because if we could theoretically build a spaceship that travels at 99.98% of the speed of light, time would pass more slowly for the astronauts on board than for us on Earth. For them, the journey might only take a few decades, while millions of years would pass on Earth. So, relative to Earth, they would have travelled through time into the future. They would return to a completely different world, assuming humanity even still exists then. However, my title for this video wouldn't be entirely accurate if that were possible. All of this was quite theoretical, and in practice, it's something else entirely. Accelerating to such a speed for such a long journey is, according to our current understanding, absolutely impossible. To give you an idea, let's look at what we humans have actually achieved so far. The fastest object ever built by humans is the Parker Solar Probe, a space probe currently orbiting the Sun. It reached a speed of about 635,000 kilometers per hour. That's incredibly fast. At that speed, you could fly from Berlin to New York in less than a minute. Sounds impressive, right? But now comes the sobering part. This insane speed corresponds to just 0.06% of the speed of light. Not even 0.1%. And with the Parker Solar Probe, it would take us over 4 billion years to reach Andromeda. And let's remember, the Parker Solar Probe is unmanned, tiny, and carries no people, no life support systems, and no fuel for the return journey. It is literally the best we've managed with state-of-the-art technology, and it's nowhere near enough. However, there are various propulsion approaches with which we might even be able to approach 70% of the speed of light. There's the ion drive, for example. We already use this technology in some space probes. It's extremely efficient and can accelerate constantly over long periods. The problem? The acceleration is minuscule. An ion drive could theoretically reach about 10% of the speed of light, after decades of acceleration. At 10% of the speed of light, we would still need 25 million years to reach Andromeda. For the astronauts themselves, the journey would seem somewhat shorter due to time dilation, but at only 10%, this effect is still quite small, perhaps a few 100,000 years less, still far too long. Then there's the concept of fusion propulsion. If we could use the same energy that powers our sun, nuclear fusion, we could theoretically reach 20, perhaps even 30% of the speed of light. Sounds better, doesn't it? At 30% of the speed of light, it would still take us on Earth over 8 million years. For the passengers on board, time would pass much more slowly. The journey would perhaps take only 7 to 7.5 million years for them. A difference, yes, but not a truly significant one. And we haven't even built a functioning fusion reactor on Earth yet, let alone one for a spaceship. One of the most ambitious ideas is antimatter propulsion. When matter collides with antimatter, all the mass is converted into pure energy, the most efficient energy source physically possible. Theoretically, this could allow us to reach perhaps 50 to 70% of the speed of light. That would reduce travel time for us on Earth to only 3 to 5 million years. But now it gets interesting. For the astronauts on board, time dilation would shorten the travel time to about 2 to 3 million years. Still an eternity, but the difference becomes more noticeable. But here's the problem. Antimatter hardly exists naturally in the universe, and producing it artificially requires an unimaginable amount of energy. All the antimatter we have produced so far wouldn't even be enough to power a light bulb for a few seconds. Perhaps the most fascinating concept is the Bussard Ramjet, a spacecraft that collects hydrogen atoms from interstellar space during flight and uses them as fuel. Theoretically, it could accelerate indefinitely, approaching the speed of light ever closer. And this is where the time dilation effect becomes truly dramatic. At 90% of the speed of light, only about 1.1 million years would pass for the astronauts, while 2.8 million years would elapse on Earth. At 99%, it would be only about 350,000 years for the travelers, while over 2.5 million years would pass on Earth. The closer we get to the speed of light, the more extreme this effect becomes. You might be wondering why 350,000 years, since I was just talking about decades. The difference is that I said 99.98%. Every tiny percentage point makes a huge difference. But here too, theory and practice diverge. The density of interstellar hydrogen is so low that we would need a funnel several hundred kilometers in diameter, a technical impossibility. Even in the most optimistic scenarios, with technologies we might develop in centuries, and even if we use time dilation to our advantage, we're still talking about travel times that defy our imagination. Hundreds of thousands to millions of years. That's longer than our entire species has existed. And even if we were to assume that we actually achieve a breakthrough one day, let's say we build a spacecraft capable of reaching 99.9999998% of the speed of light, and the journey takes astronauts only a few decades, we're still facing the next intractable problem. The human body. Our bodies are designed for life on Earth, not for decades in a spacecraft. Even on the International Space Station, astronauts begin to experience serious problems after just a few months. Bones deteriorate, muscles atrophy, and the immune system weakens. After 30, 40, or 50 years, catastrophic. Even worse is cosmic radiation. Outside Earth's magnetic field, it penetrates spacecraft walls, damages DNA, and causes cancer. After decades in space, astronauts would almost certainly die from radiation sickness long before they even reached Earth. And then there's the psychological aspect. Decades in a metal capsule, confined with the same people, without fresh air, without a sky. Just walls and the endless blackness of space. Even brief isolation leads to severe psychological problems. Over decades, it would be unbearable. And even if we were to solve all of this, the astronauts would be traveling into a future they don't know. Even if the journey only takes them 50 years, millions of years will have passed on Earth. Humanity would have long since ceased to exist. They would have no one to return to. I haven't even listed all the problems in this video. There are many more. This is the brutal reality. Andromeda is unreachable because of physics, because of energy, because of our biological limitations. because of time itself. The laws of the universe have built a wall around us that we can never break through. As always, I hope you enjoyed the video. I would really appreciate your support, and I'll see you next time.